Good morning, everyone. Today, I will present Experiment 5.1, Atomic Absorption Spectroscopy, commonly known as AAS. In this experiment, we will learn the fundamental principle, operation of the instrument, quantitative analysis methods, and interference effects in atomic absorption spectroscopy. We will also apply this technique to determine the calcium ion concentration in water samples. Atomic absorption spectroscopy is a widely used analytical technique for detecting and quantifying metal elements in different samples, especially environmental and water samples. The main purpose of this experiment is to understand the fundamentals and operation of AAS. First, we learn the basic principle of atomic absorption spectroscopy. Second, we study quantitative analysis methods such as the calibration curve method and the standard addition method. Third, we examine interference factors that can affect the measurement accuracy. Finally, we apply AAS for water quality analysis, specifically determining the amount of calcium present in water samples. Let's discuss the main principle of atomic absorption spectroscopy. It is based on the absorption of light by free atoms in the gaseous state. When atoms or elemental ions absorb radiation in the ultraviolet or visible region, they produce a characteristic absorption spectrum. However, before absorption can occur, the sample must first be converted into free gaseous atoms. This process is called atomization. Different atomization methods can be used, such as flame atomization, electrothermal atomization, inductively coupled plasma. In this experiment, we will use flame atomization. This slide shows the atomization process used in atomic absorption spectroscopy. In this experiment, we use the flame atomization method. The flame is produced by the combustion of an acetylene and air mixture. The flame temperature is around 2,300 degrees Celsius, which is high enough to break molecules into free atoms in the gas phase. Most atoms produced in the flame remain in their ground state. When a beam of light with a specific wavelength passes through the flame, atoms that have the same absorption wavelength will absorb this radiation. As a result, electrons in the atoms move from the ground state to the excited state. Each element absorbs specific wavelengths so we can identify and measure specific elements such as calcium. The quantitative analysis in AAS follows the Beer-Lambert law. The equation is A equals log P, P equals epsilon B C, where A is absorbance, P is incident light intensity, P is transmitted light intensity, epsilon is the molar absorptivity coefficient, B is the path length, C is the concentration of the analyte. This equation shows that absorbance is proportional to the unconcentration of the analyte. Therefore, by measuring absorbance, we can determine the concentration of metal ions in the sample. The first quantitative method used in this experiment is the calibration curve method. In this method, we prepare several standard solutions with known concentrations. Then we measure their absorbance values using the AAS instrument. Next, we plot a graph of absorbance versus concentration. If the system follows Beer's law, the result should be a straight line described by the equation y equals a plus bx. The second qualitative method used is the standard addition method. In this method, we take equal volumes of the unknown sample and place them into several volumetric flasks. Then we add different amounts of standard solution containing the analyte. After dilution to the same final volume, the absorbance of each solution is measured. Now I will explain the chemicals and instruments used in this experiment. First, let us talk about the chemicals. In this experiment, calcium chloride is used to prepare the calcium ion standard solution, sodium phosphate, sodium chloride, EDTAHCl, tap water, mineral water, and unknown sample. Next, we look at the instruments and glassware used in this experiment. A 100 milliliters beaker is used to dissolve the chemical. A 250 milliliters volumetric flask is used to prepare the standard solution. Accurately, In addition, deionized water is used as the solvent for preparing all solutions. Now we start the experimental procedure. In experimental step 1, first a 500 ppm calcium ion stock solution is prepared using calcium chloride dissolved in deionized water. From this stock solution, different volumes are taken and diluted to 100 milliliters in volumetric flasks. The volumes 0.1 milliliters, 0.2 milliliters, 0.5 milliliters, 1 milliliter, 1.5 milliliters, taken from the stock solution. Each of these solutions is diluted to 100 milliliters de water. We obtain standard solutions of 0.5 ppm, 1.0 ppm, 2.5 ppm, 5.0 ppm, 7.5 ppm. In experimental step 2, 0.1 grams of the unknown sample is placed in a 100 milliliters beaker and dissolved with 50 milliliters de water. The solution is transferred to a 500 milliliters volumetric flask. 3 milliliters of concentrated HCl is added. Add D water to the mark to prepare unknown I. Then add 2.5 milliliters of this solution in 100 milliliters to obtain unknown 2. Next, we prepare solutions for the standard addition method. 2.5 milliliters of unknown I's placed into several 100 milliliters volumetric flasks, and 0.25, 0.5, 0.75, and 1 milliliter of 500 ppm calcium ion standard solution are added. Each solution is diluted to 100 milliliters with deionized water and labeled A, B, C, D, and E. Their absorbance will later be measured to determine the calcium concentration in the unknown sample. Now we will study interference in calcium measurement by preparing solutions. First, sodium interference. Mix 1 milliliter of 500 ppm calcium with 50 milliliters of 2000 ppm sodium. Dilute to 100 milliliters. Second, aluminum interference. Mix 1.00 milliliters of 500 ppm C squared with 1.0 milliliters of 1000 ppm Al cubed. Dilute to 100 milliliters. These test how sodium and aluminum affect calcium absorbance. Third, we study phosphate interference. We take 1 milliliter of 500 ppm calcium and 10 milliliters of 100 ppm hydrogen phosphate. Then dilute to 100 milliliters. This shows how phosphate affects the calcium reading. To minimize this effect, we add EDTA. In this solution, 1 milliliter of calcium, 10 milliliters of phosphate, and 40 milliliters of 1000 ppm EDTA are mixed and diluted to 100 milliliters. EDTA binds the interfering ions, reducing their impact on the measurement. Now, we operate the atomic absorption spectrometer. First, we use the calibration curve method with 2.5 ppm calcium ion to adjust sensitivity and record absorbance. Repeat 5 times if readings vary. Next, measure absorbance of blank, 0.5, 1.0, 2.5, 5.0, and 7.5 ppm calcium ion. Repeat 5 times for accuracy. Finally, measure the unknown sample and also analyze tap water and mineral water, recording each 5 times. Next, we determine calcium using the standard addition method. We measure the absorbance of solutions A to E 5 times and calculate the average to plot a graph and find the calcium concentration in the unknown sample. Then, we study interfering ions. First, measure 5.0 ppm calcium ion without interference as a reference. Next, measure 5.0 ppm calcium ion with sodium, aluminum, or phosphate ion. Comparing these shows how these ions affect AAS accuracy. During the experiment, several precautions must be followed. First, prepare all solutions carefully using clean volumetric flasks to avoid concentration errors. Second, must inform 2TA before open the acetylene and ignition. Third, Fill the beaker with de-water to prevent dry burning of the instrument. Fourth, use clean pipettes and glassware for each solution to avoid contamination. Fifth, always dilute solutions to the mark in volumetric flasks to ensure accurate concentrations. Finally, total of 18 samples will be tested using a CS. Now let's go through some discussion questions from the experiment. First, why is the atomization process important in AAS? Briefly describe it. Second, between the standard addition and calibration curve methods, which is less affected by complex sample matrices, and why? Third, what chemical interferences are common in AAS, and how can they be minimized? Fourth, what is the light source in AAS, and how does it work? That's all, thank you.